Remaining are the joining first time, right? Okay, so we have started the strength of material in the last class. So some parts that we haven't touched upon in the last class, so that will do in the first today, and after that we'll solve some problems. So in the last class we will first quickly recap what we have did, and then we'll start for today. So in the last class, initially we started and we saw like in strength of material where we usually work upon. So it will be in the starting of the in the end of the we usually work in the elastic zone for the strength of material, and after that we saw the some basics of the stress strain, and hmm, and we saw the difference between the stress and the pressure. And after that we have seen like some examples where FBD we have saw how to draw, and uh, 1 minute, we saw the ability and find the stress on the different elements, and after that Hooke's law, Poisson's ratio, relationship between different elastic constants. It is valid for the isotropic we have seen. Then we have seen the uh, number of independent elastic constant needed to define the whole stress or strain matrix. We have seen that. Mm, and we saw then solve some problems, and so for today we will start after that. And the thermal stresses introduction we have seen. So actually to go more deeper in the thermal stresses, so for that we have to go for the elongation part first. So that's why we are doing that first, and after that we'll go more deep in the thermal stresses. So from here I will start. So as we know, like let's suppose this is a prismatic bar, and okay. So this is a prismatic bar, and one load of P is working there, and its cross section area is A. So and its Young modulus is E. So what would be the stress there? Hello.
P by.
P by A. Yeah? So stress would be here P by A, and strain would be, let's suppose after this elongation is delta L. So delta L and initially length is L. So delta L by L would be the strain here. And now if and also we know like stress upon strain is, sorry, stress upon strain is Young's modulus. This is by the Hooke's law. So we will uh, take this here, and P by A and divide by delta L by L would be the Young's modulus. So when we solve it, delta L will come PL by AE. So here we simply find like delta L would be the PL by AE. But here that we are able to do because here we considered as the let's suppose Young modulus is constant everywhere. First assumption is here that, and second it's a prismatic bar, and area is the constant for the whole length. So that's why we are able to do like that. But now cases will come like when area will be varying like that, tapered bar would be there, and for example force will vary, we hang it vertically and due to the self weight, so here force will vary, right? Hello.
Yes.
So here p would be the function of x, and here what is the problem? Here area is the function of x, and let's suppose we have taken the bar here, and this is the rotation, and we rotated it. Now due to the centrifugal force, uh, force would be the function of x from here, right?
Yes.
So for these cases we are not able to do this way. So for that quickly we will in 15 to 20 minutes see, and uh, then we go for the problems. So for the first case we will see that we will take the tapered bar. So anyone knows the formula? Directly formula some can remember, but we will see first because it may vary in different way also. So anyone knows what is the elongation of the tapered bar? Like let's suppose I will draw the first, then I will ask. So its diameter is changing from small d1 to capital D2, and we are applying force P here, and Young's modulus E is constant here. So anyone knows what is the elongation for this? Okay. So here what is the problem that we are not able to use that formula? Anyone? Hello.
Yes, sir.
Mm, Here in this tapered bar, what is the problem that like we are not able to directly use this formula for the elongation in the length due to this load?
Sir, area is changing in every section.
Area is variable. So we have whenever there is some anything is variable, like it there may be load may be variable, area may be variable, or either this Young's modulus is this all they may also be vary may also be vary with the length, and if anything is variable then we have to go with the elemental formula. Okay, we will anywhere some variation is there, we used to take the elements, right? At some distance we will take, and now we will see like if we take this element, and now here area we may consider as a constant, right? Hello.
Yes, sir.
Uh,
So whenever change is any variation is there, and we have to find the things, we go for the integral things. We used to find the things by the integrations. So at a distance of, let's suppose this is the distance at x distance, we took this uh, dx, element of dx we have took. So anyone can tell like here diameter is d1, here diameter is d2, and this total length is l. So what would be the diameter at this distance of x? So I want to know like mm, what would be the diameter at x in terms of d1, d2 and l. Can anyone tell? Are you getting what I'm saying?
No, sir.
Yes.
Could you please repeat it again?
I am saying like here we have to find the area first. So in order to get that area, we want to know like what would be the diameter at the distance x from the D1 in terms of D1, D2 and L.
Sir, we'll use similar triangle.
Similar triangle also we can use, and here we can easily get because it's linearly varying. So here we can get like diameter is increased from D1 to D2 in the distance of L. So what would be the rate of change of diameter? D2 minus D1 by L, right? This would be the rate of change per unit length. This much diameter will be changing. So for the x length you want to get the change, so here you can simply multiply x. So what this term will be showing, how much diameter would be changed, means delta d it will show for the x length, right? And here it is already d1, so simply we can write this. Is it okay to everyone? Hello.
Yes, sir.
Yes, sir. Yes.
So we have found the diameter at the distance x, and now and rest other things are constant because e are constant here, p is constant, and this only is changing. So for this small element, what would be the change in length? Let's suppose this is the let's put this is the dl. So what would be the dl for this small element? When equilibrium diagram will make, this will be p, this will be p. So p, and what is the length of this? Dx, right? PL by A. Area we can take from here now. So area would be pi dx square, and E is the constant. Is it this equation is okay to everyone, right?
Yes, sir.
Huh.
So now simply what would be the total delta L? We will integrate this equation, first equation, from where to where? Let's suppose from here we will start, and here to here, from 0 to L we can say. Hello.
Okay.
Sir, did you start recording?
I think I have started that. I have checked first. Once again, I will see. Yeah, yeah, it is happening. So we will integrate this from 0 to L. Here, in order to keep it simple, d2 minus d1 by L, d2, d1, L, all are constant here, right? Because these are not going to change for a equation, for a task question. So in order to keep simple in writing, we will make this as a constant k. So it would be the p dx by pi d1 plus kx square e. Correct?
Huh. Huh, sir.
Now we will simply integrate it and put the limits, and then we will get. So now we'll integrate. So anyone tell what would be the integration for this? P is the constant here. P by pi we will p by pi e we will take out, and integration of 1 by x square, what it is? Hello.
Huh, sir.
Integration of 1 by x square is similar, na? It would be minus 1 by x, right? So
1 by
minus
X.
d1 plus kx, and here k is there, so k will come here, correct?
Correct.
Huh.
Now we'll simply put the limits 0 to L, and it will come. So now limits will put, and it p by pi e minus we will put k will take it out, so it will become minus 1 by here when we'll put L here, so L 1 minute, I will again put cage d2 minus d1. L and L will cancel out, right? So d1 will get cancelled. Minus 1 by d2 will come from here. That I will directly write. Got it or not? This one.
Yes, sir.
So minus 1 by d2 will come from here, and when we'll put 0 here, so directly it will come plus 1 by d1, right? Hello.
हाँ sir.
I think k here I missed. Anything? No p. Anything missing here or what?
It's actually correct
It
only, sir.
is there. Okay, okay. Here actually we are taking diameter, right? So pi by 4 would be there. I think 4 is missing. Here we did pi d square, right? So 4 would be here.
Yes, sir. Yes.
Pi by 4. So 4p will come. So now just simplify, we will and get it will come 4p L by pi d1 d2 e. Just simply we will take and put the value of k. This will cancel out, right? This d2 minus d1 part, because it will come here, d2 here, d2 minus d1 will get cancelled and it will come, right? Hello.
हाँ sir.
Yes.
So one question will come like if we equivalent rod we want to make with the prismatic with circular diameter and this tapered circular diameter. This is d1, this is d2, and this is d. So then relation between d and d1 d2 it will ask. So what would the relation, anyone can tell quickly? Length and Young modulus is same for both. I will wait for 1 minute. This is the question for first question from here.
In terms of how should we relate, sir?
Uh, Equivalent means like uh, all other property would be same apart from this d1 d2, and means diameter all would be the same, means when we are applying load p here and p here,
Means reflection is same, sir.
then that elongation would be the same in both. So we equivalence means here is the same. So one rod is this A and another one is B. So A and B would be the equivalent if the when we apply same quantity of the same load, and it will show the same deflection, same elongation. So when it will be the same elongation, what is the relation between D1 and D2? That I want to ask.
D equal to root d1 d2.
So here would be the geometric mean of this, right? D1 D2. So anyone other person? Any other answer? Okay. So what would be the elongation for this prismatic bar? Simple, this formula we can use, right? So delta L for A would be the PL by A. PL by A. What would be the area of this? Pi by 4 d square, right? Pi by 4 d square. So and E. Now coming to the delta L of this B. This would be the same, this formula, right? 4PL by pi d1 d2 L. Sorry, E. Now, when this both would be equal, 4PL pi E. 4PL pi E is here. So D square should be the equal to the d1 d2. Correct or not?
Yes.
So this would be the relation. So when we take this out, it will become under root of this. So this is the one simple thing. Now coming to the next. So if anyone want to take the screenshot of this, take it, and then again we'll go quickly. Okay, should I go forward? So now we will see the elongation due to the self weight, and let's suppose this is the one prismatic bar. Here what would be the bearing? P, either A or E. What is bearing here? Hello. Gravity would be this side. So this is the here elongation due to the self weight. Elongation due to self weight. So at any distance, let's suppose we are measuring distance from the downside here. Let's suppose x starts from here, and this whole length is L, and young modulus is E. So let's suppose this is the dx length here. As we go up, so mass in downside to the this element would be more, right? Hello.
Yes.
Yes, sir.
Uh,
Yes.
so what at an whatever element we have took, whatever mass is downside of that part is the load acting upon that element. This we have to think. Actually, this is the simple problems. What will happen, like now they will merge two things. Now they will hang this tapered bar uh, vertically, like this way. When this will happen, then problem will start. Sorry, this way. Here we have, you have to take care of both things, area along with this elongation due to self weight, right? So then it will more complex problem will happen. So that's why we are doing this first, and then we'll do the problems. So what would be the weight of that part? Let's suppose area of this is A. So can anyone tell?
Sir, should we separate from two axes like a part of xx and part of yy?
Not getting what are you saying?
Actually, I am telling that should we separate it into the two axes like xx axis, weight on the xx axis and weight on the yy axis? The weight will act on the xx axis and yy axis like that.
Mm, Actually, which XY we are axis I haven't made here, na? What way you are
Like
telling?
one would be the portion you mentioned, that dx, that linear portion is
Hmm.
xx. I mean that line will maintain the xx and the vertical line will maintain the yy. Wait.
Let's suppose
Ha,
this
ha,
is
ha, ha. Ha,
this Y you are saying this is X, okay?
ha, ha.
And then
Then y into x, the weight will at
oh,
y
you
equal
are
to a
telling about
into
the like what would be the weight of this
ha,
part you
ha,
are telling, right?
ha, 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 ha.
Okay, okay. One. So let's suppose the density of the material is rho. Huh? So you have to find the weight of this much part.
Ha,
Hmm?
ha.
So now it is easy, right? W of x would be the rho and the volume. How much volume is this? Area is this and x length.
Huh.
Rho
Then A
ax.
into X, AX, yeah.
Rho ax. This would be the
Huh.
weight, and this much weight is acting upon how much length? Dx length.
DX length, yeah.
P L y
So
a
G
x.
would come.
Huh?
So
Oh,
since it is
okay,
weight,
okay.
G would come.
G is also there. So this is the mass. Sorry, this is the mass, and when you multiply with gravity, it will become force. And W L by A. Area is constant here. Area may also vary, right? That I have shown here. So
Huh.
if that is happening, then you have to that also put in the terms of x. It will simply the
Huh.
integration problem there, right?
Huh. Huh. Huh.
So
A
in that case, like since the equation of A is same in numerator and denominator, will it get cancelled? Sir?
what?
So if area is changing, like in that case, if we are substituting the equation of A in numerator and denominator, it will get cancelled, right? Sir?
Here you are saying as of now, na?
In tapered bus.
In tapered. In tapered, actually, what problem will come, na? You will be finding problem like what would be the volume here. In tapered, we can get, but if it would be varying in some another fashion, then the volume of the material is difficult to find here, right?
So, but actually,
So
since it is in both numerator and denominator, like it will be independent of the area, right? Sir?
actually, here whatever for the elemental we are doing, then it here it would be for the element here, right? Let's suppose for any distance x you are saying. So for that x, you are putting the x of this part, right? Only this area, sorry, ax. Getting my point or not? If here,
Yes. Yes.
and whatever here we have tried to use put here also, then we will put the area in the terms of x only. Here only we will put. That also will keep on integrating. Here directly simply we have multiplied all for the here bar is this way. So here how volume we have found? Simply multiplied a into x. But if it this in if this would be in the this fashion, so we cannot be like a into x, right? We cannot do like this
Yes.
way. So then what we have to do? We have to find the area here, ax here at the distance x for the dx length, right? So
Yes.
here we will first find the dv. dv would be the what? Ax into dx, right? Hello.
Yes.
So it would be the some very complex problem. It generally it will not come because here 2-3 times you have to put integration, right? So this would be very complex problem because you have to first find the weight here in the function of x, and then again you have to here put do pl by a. Here also dx will come. So it is very complex. Getting or not getting?
Yes.
Uh,
Huh.
that's why here a prismatic one only come usually. So pl by a e. Now this would be the dl. So we will simply, in order to find the delta L, we will integrate this from x will vary from 0 to L. Rho ax, rho a gx dx by ae. Here a will cancel because here it is constant. No? Both are same. So rho gx, rho g by e, and integration from 0 to L x dx. Correct?
Yes.
So it will become when we will integrate this rho g L square by
E. Huh.
2e. L square by 2 will come now.
Huh. 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 Huh.
So it will become this. Now here now what conclusion you can get from here? like if this length is 2 meter for the one and another one for 4 meter, then what will the elongation? Elongation is proportional to the L square, right? Hello.
Yes.
So change in length varies square of the uh, length. So this is the first conclusion. And second, whatever be the area of this, it is not function of the area here. So whatever would be the area, elongation would be the same due to the self weight. Correct?
Yes.
So now one question we can try. Let's suppose this is the bar, and we have applied the load P here. Hello?
Yes, sir.
And its weight is W. So what would be the answer? Just we can simply get by the elongation due to this and elongation due to the this load PL by AE. This would be right. For this simply PL by AE, and for this W. In terms of W, if you want to make it this, what will happen? Rho.
WL by
Uh, what you are telling? Tell.
WL by 2 AE.
2A, right? So now let's suppose same W load we have applied not in self weight, now simply weight we have applied. Then what would be the this elongation? WL by A, right?
Huh.
Getting what I'm saying? I'm saying like
Mhm.
this is due to the self weight. Now self weight remove, not no self weight is there. Now same W we will apply, but as a form of load. Then what will be the elongation? WL by AE. Hmm?
Mhm.
So what is
Yes.
the what next conclusion from here? Elongation due to self weight is half of same point load, right?
Sir, one thing here, same point load means,
Means
uh,
let's suppose here its weight is W. Now again we have applied W load here, right?
okay.
So let's suppose you have calculated and found like due to self weight elongation is 2 mm.
Uh,
Now now you don't want to calculate this. Now directly you can say it would be the 4 mm.
mm. Huh.
Got it or not?
Huh, huh, huh. Got
So
it.
simply total elongation would be the 6 mm.
Huh, huh, huh. Got it.
So this is the conclusion from here. Any doubt?
Sir, one thing that for previous equation, what did you tell the function of area? Like previous.
Here you are saying. So
No, 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 no.
uh,
On this slide. Yeah.
uh,
Del L values L square and del L not equals to function of
so
area.
here in the function, now let's suppose here one problem area is the 1 mm square,
Huh,
and in another problem area is 2 mm square.
huh.
So would there be any change in the delta L or not?
Yeah, there would be change.
Why? Whatever, let's suppose here you will put 1, and now in denominator also you will put 1. 1 get cancelled. Either 2 you will put 2 here, 2 here, 2 will again get cancelled. Hmm?
Mhm.
So area will get cancelled at the end. Area is not affecting the elongation here.
Okay. Okay, now got it.
Huh. So that is the point here. Okay. Any other problem, or should I move forward?
Okay, sir.
Now let's suppose this is the bar and we are rotating it from here, omega. Got it?
Huh.
So now what would be the self weight? First of all, tell me like what would be the force here? How will you calculate?
Should we think about with like twisting motion
No, 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 no twisting would be here. Anyone? Hello.
What is the question?
Question is like this is the rod of length L and we
Okay.
are rotating from this axis. So we have to find the elongation due to elongation in the bar. What is the delta L? That is our problem. So in order to
Means,
find what?
elongation in the bar due to rotation, sir, or
Due to rotation.
stress or rotation, sir?
Huh?
Due to stress or rotation.
Actually your voice is missing. What are you saying?
Sir, you are asking about elongation in a bar, no, sir?
Elongation in the bar due to the rotation. So due to rotation what will happen?
Decrease in volume.
That will okay, but there are particles, so those particles will feel the centrifugal force, right?
Yes, sir.
So that centrifugal force will come into the picture here. So how now here I want to see like let's suppose this is the element, okay? This is its length is 3x and its total length is L from 0 to L we will say. Okay? Hello.
answer?
Yes, sir.
Now let me know like which part will put the centrifugal force here. Area is A and its length already I told X, L. Let's suppose from here we are measuring it is X, not till here, till here. It is X and its length is dx and total length is L, so this would be the L minus X, right? Hello.
Answer.
And
Yes, sir.
we know the centrifugal force, let's suppose P we are telling, it would be the mr omega square, right?
Huh. So
Yes, sir.
mu omega square
What is mu?
by huh?
Here what mu h came? Okay, mu your density you are telling, I think.
Huh?
Rho we are saying, rho is the density, okay. So here we'll put rho. Okay, first of all let me know what would be the mass here. Anyone? Mass would be the rho area. Now it will become the distance. Which distance? This x will come or L minus x will come? That I want to know.
L minus x, sir.
So because which part will be pulling this part element? This one,
L
right?
minus L,
Uh,
L
so
minus
L
x.
minus x will come first. Okay, this is the mass. Now what would be the R? Because here you
Sir,
would be committing mistakes.
the x part would be the r because sir which one is rotating, sir?
Okay, any other answer for this? For the
X.
Sir, it's
centrifugal.
omega.
Uh,
It's omega, no, sir. Omega square.
okay, omega square is omega square. No issue is there. What is the R?
R is the rigidity modulus.
Huh?
Rigidity modulus, sir.
No. R would be the like this is the one, let's suppose, and here is the mass m, and this is radial distance is r, and we are rotating at omega speed. So what would be the centrifugal force here, or centripetal force requires to rotate this m r omega square, right?
Yes, sir.
So r is the radial distance from here to the center of gravity of this mass. That is the main point I said. Center of gravity of this part. So mass. Now some hint would be there.
It should be x plus dx by 2.
1 minute. Again, you have somewhat closer, but why x plus dx?
Sir, it would be just L. Won't it be, sir?
Just L means here. Here it is the CG. Why?
Huh?
In this element,
Mm.
this is
L or
the
L by
element.
2,
One
sir,
minute, one
because
minute. Let me know. This is the element, and what force is acting here? Force is due to this region.
this pulling force.
This is the region. This is the total mass due to which here force is coming, right? So what example I have said, I have given to you, like this is the point mass here m, and this is the distance r, and omega it is rotating. So what is the usually centrifugal force is here, m r omega square, and its a center of gravity due to the point is only this point. So what r is distance is from r is known as this, keep in mind, otherwise in mechanics you will put all other wrong answers. R is the distance from center of rotation, sorry, axis of rotation, not center, axis of rotation to the CG of rotating mass.
Hmm.
Now somewhat
So,
clear what we have to take?
yes, sir, would it be L minus R by 2?
L minus, no, R, why R?
Sir, R means that radius, and then
No,
as
no,
as
what
that
is the
force
rotating
would be
mass
acting
here?
upon the.
What is the rotating mass? L minus x part is rotating mass, right?
Uh-huh.
So what would be the center of gravity for this much mass? Center of this, right?
Half of that length.
Half of L minus x by 2. But from where we have to take center of rotation, sorry, line of rotation, or sorry, axis of rotation. This is the axis of rotation, na?
Uh-huh.
So from here to here, what is the distance? That is the R.
So that would so that's why I told that would be L by 2, because x plus L minus x would be just L, and then
X
half of it.
plus L minus x by 2.
Uh, oh, okay. Now I got it.
Is it clear
Actually,
to
I
all?
thought that.
You are telling L by 2,
I
not
thought.
it would here, na? Because I have put the dx here, it doesn't mean it is the mid, na? Now
Now
it
I
is
got it.
clear or not?
Now clear.
So what it will come? L plus x by 2 it will come, right? When we solve it. Hello.
Sir.
This is okay now.
हाँ.
So now we can easily put, right? Mass we knows, r now we have r value of r we knows L plus x by 2, and omega we will know, right? So
Now T would be like m omega square,
one
L
minute, one
square
minute.
minus x square
So first of all
by
we will
2
find the dl. Why we are finding dl?
for
Because we are finding
the
the
elongation.
elongation in the small part, right? Dx. So it would be the m is what? Rho
Mass.
a
Oh.
L minus x, right? Rho a L minus x. This much part is rotating, right? Is it clear or not?
So the centrifugal force is not created by the mass which is present in before this.
No.
Uh,
This will not be doing anything. Centrifugal force is what? What is rotating outside? A centrifugal force on this element you have to find, right? So this element, which mass is pulling this element? Only this mass will be pulling, right? So this mass you
yeah.
have to take, and in the centrifugal force, what is the R? R, this line you have to take care of this. distance from the axis of rotation to the center of gravity of the rotating mass. Whatever is pulling. So this R is very important here.
Sir, but there is no effect of the remaining mass, sir.
Huh? What?
Which means there is no effect of the remaining mass, sir, on centrifugal force.
No. Whatever mass is here, this will be pulling another. Let's suppose this part you are taking. So this part would be pulling this part behind this. Okay. For every mass is pulling. It's just beside. But we have taken one just a small part, na. So we are taking this much part for this dx. Uh, who would be pulling? This much mass is pulling for this, and for this outer part, no one is pulling. So it would be here. Getting on it. That's why we are integrating from here to here.
Yes.
So we simply masses came from here, and L R would be from here. L plus x by 2, and omega is constant, and this is the dl. So in order to get the delta L, we will simply integrate from where to where. What would the limit here? Anyone?
This is force, sir, actually, like, I think.
Oh, sorry. So this is the force P, and L would be the dx, right? Small element. This you are getting. Why I am putting dx here?
Yes, the length of the section.
Length of the section. Whatever we are is pulling out. So PL by
Then the limit would be 0 to L, sir.
Limit from here 0 to L. Because in the rotation limits only you will commit mistake. Now integration is simple, right? You can do. So here what would be the problem? Like it will ask like what would the stress at any section? It may ask at the end of the formula, or it will say like what would the maximum stress. Okay. So this is the formula. I would be you will do this in the home. So I will telling you the answer for this. When we solve, it will come rho omega cube. Sorry, rho omega square.
L square by 3ay.
It will come L square x minus. Sorry. How much it will come? Okay, when we integrate it, it will come like this: x cube by 3. A limit will put from 0 to L. Okay. So now we'll simply put the limits. It will come rho omega square L cube by 3a. Okay. This is the total elongation. And at any distance x, if you want to find, it will come like sigma x would be rho.
Sir, 3e or 3a, sir? Because a
No,
won't.
here a will diminish, na. A here. Getting or not?
Yes, sir.
It will cancel out, na. Area is same, not changing.
Oh, okay.
So at any section x we can easily find, right? There we need not to take the integration.
I haven't followed that, sir. So what?
Px you can easily get, na. Px at any section x, what would be the force there? You can get, na. That I am asking you. This is the px, right? This much part. This is the px, right?
Yes.
At any section x, what would be the centrifugal force? This would be, na.
Sir.
I told na initially. So this would be the force. So what would be the stress at any section? Px by simply a. Area at that section, right?
So while we take the dx element, we will be multiplying the dx with rho into a for mass element. Why did you take that L minus x here?
Here, this much is telling mass of this much part, here to here, rho a, and this much length. For how much length is this mass? L minus x length, right?
What I'm asking is why do we take that L minus x portion? We will be taking the dx element, mass of the dx element, isn't it?
No. Here centrifugal force. What centrifugal force is pulling? This is the part where you have to find the force. You have to find the force, and which force is acting here? Centrifugal force. And what is the centrifugal force? Actually, now same thing you can appreciate from here. Let's suppose this is the strain, and this is the mass here. Let's suppose one iron ball is there. You are trying to rotate from here. Okay, this is your hand. Hmm? Sorry, omega. So, what would be the mass of this? Let's suppose this string is plastic string. Hmm? So, what force you if a mass of the ball is m? So, what is the force here? Whether you have to you are taking this is r. Let's suppose this plastic string is of 100 gram, and this mass is of 2 kg. So, whether in calculating centrifugal force you take to this 100 gram or this 2 kg. Hello.
Okay, so we'll take that.
Whatever mass is pulling, that you usually take, that you have to take na, because this mass, this force is mr omega square, right? This mass you have
Okay,
to take. So
okay, sir.
that's why we are taking this.
Also, the mass which is pulling it outwards from the.
That mass you have to first set. This actually this part come in the that in mechanics. So due to their concepts are somewhat no more less clear. The, actually there we usually takes what is the centripetal force, that is the centrifugal force. So that way somewhat more problematic. There not these type of problems will come. They are simply one mass is there, mr omega square we used to take, and forget where is the cg, where is the everything. So that is clear, right? So px we can easily get from here, like px we can get, and area is same here, so a will get cancelled. So stress at any section we can easily find, right? That I'm asking to you. Hello.
Yes.
Hmm. So what would be the stress? Rho a, L minus x, L plus x would be the L square minus x square, right?
Uh,
And omega
सर
square. Yeah.
सर इट इज बेनिफिशियल टू लर्न दिस और मतलब कि उसी वक्त सॉल्व करें तो ज्यादा अच्छा है.
Why to learn? Now just let's suppose rotation axis would be this. Now learn what would be the formula. Tell.
हाँ सर, ओके सर, ठीक.
Actually, in whole syllabus, how much formula you will learn? You cannot learn everything. Whatever is necessary, that you must have to learn. Here it is a conceptual part. Like you can easily find the distance and calculate.
या सर, ओके सर.
So it would be what will come? 2 will come, and A will get cancelled, and simply it will come, right? Clear or not?
as
Okay. So this main this is the part that I want to tell. So this part finished. Now I want to Hooke's law. Last class we have seen. So and let's suppose this is the body, 3D body. So here it is applying sigma x, here sigma y, and here sigma z. Okay. So now I want to know the what will be the strain in the direction x. due to this loading. Okay, is it clear what I'm doing?
Yes.
uh, so here strain will come due to all these stresses, right? Hello.
Yes, sir. Yes, sir.
Hmm. So first of all, direct stress will come. It would be the sigma x by E. Now the effect of this will come. Why? Why effect of this will come? Anyone can answer?
So like
Since whole body is a single unit, so deformation in one will मतलब change मतलब कम कर देगा ना दूसरे में
So how?
volumetric.
What would be the value of this? Due to this, what will be the change in the x? How will you find?
सर मतलब lateral dimension में कितना change हो रहा है?
Here due to y it is the lateral dimension, huh? So here Poisson ratio will come into the picture, right?
Yes, sir.
Hmm. So what would be the formula for that?
Minus mu
Hmm.
sigma y
By E.
e.
This is clear. If anyone not getting this, why, how it came, then I can tell. Need not to tell, right? Mu sigma g by E. In the similar way, we can write minus mu sigma x by E here plus sigma y by E here and minus mu sigma g by E here. Here minus mu sigma x by E plus minus sorry minus mu sigma x y by E plus sigma z by E. It is clear, right?
Yes, sir.
That I told because now we are going to solve the problem on this on the basis of this. So that's why I have told this. So first see this problem and try to solve because read this problem and I will giving you 2-3 minutes and then we'll start. And if anyone is solving, then let me know the answer. Okay. Hello. Are you trying or not?
yes, sir.
Okay.
Sir, E is 105 gigapascal.
Okay, mu. I think A is correct. What is the mu?
Finding, sir.
Okay. What you told? 1 minute. Answer tell.
105.44 gigapascal.
Anyone who are getting, and let me know their answer. Okay. Whatever different would be also okay. Tell me.
Sir, mu is 0.336.
0.3, right? Okay. Someone other is trying, or should I start? Okay. We are starting then. So first of all, we'll write the given data. Whatever is given. Copper bar of initial diameter is given 10 mm, and length is initially given is 100 mm. So tensile force is applied. Let's see. This is sample. 10.6 kilonewton, and delta L is given, right? So area is given here. How much area is there? The diameter is given. Area how much calculated? If you calculated, how much area is given? 5 by 4. 10 square.
78.54.
78.54 mm square, right?
Yes, sir.
So now delta L is given, and L not we know, so strain from here we can calculate, right? First we are trying to find A. So what will be the strain? By 100, right? Hello.
Yes.
So how much strain will come? It will be, so go there, 1.28 into 10 to the power minus 3, right? So strain we know, for in order to find the Young's modulus, what we again, what remaining we have to know? Stress, right? Strain we know, the stress, if we know the stress, then stress by strain is Young modulus.
Yes, sir. Yes.
So what would the stress? 10.6 by this area, 78.54. This is in the kilonewton, that keep in mind, and this is mm square. So how much it is coming?
134.96 megapascal.
Here tell okay. Let's suppose if you put in the into 10 to the power 3 newton, then it will become megapascal. How much it is coming? 134.96
96.
megapascal. Now, what is the value of Young's modulus C? Sigma by epsilon. Sigma we know is 134.96, and it is the megapascal, and here 1.28 into 10 to the power minus 3. So minus 3 will go up, it will become into 10 to the power 3. So what value? 105.44, right?
Yes.
So when divide, so approximately it will become gigapascal. So this way we have to do. And next what we have to do? Any idea? Now we are going for the Poisson ratio. What is the Poisson ratio?
lateral strain but a longitudinal strain, negative of.
Negative of lateral strain by longitudinal strain. Longitudinal strain value we know. This is the longitudinal strain. Longitudinal means in which direction load is applied. That is known as longitudinal. Okay. That keep in mind. Otherwise, sometimes your load is applied in this way. You are looking for the length direction. That is not longitudinal for that load. In so longitudinal means in which direction load has been applied. That is the longitudinal direction. So a load is applied here. So that this value we know. This we have to find. Huh? So here diameter initial diameter is we have initial diameter, but final diameter we don't have, right? Hello. Hello.
Yes,
So
sir.
sorry.
Yes.
Am I audible or not? Hello.
Yeah, you are audible, sir. Hello.
Okay. So what is the that lateral strain? Lateral strain is the change in the diameter by initial diameter, delta d by d. And what is this? Delta L by L. So here we don't know delta D, otherwise remaining we knows. So how we can find this delta D? Any suggestion for that?
सर डेल्टा डी दिया तो हुआ है
Where it is given?
4.3 माइक्रोन.
Oh, sorry. I think I haven't given. Okay, it is already given here, so it is very simple then. So now here we will put in the same units. What is there? Micron. So we'll convert to the mm. So how much mm? 0.0043, right? Divided by 10. It is reduced, so it would be the minus here. Okay, minus. It is the 10 and the delta L is given. I think the point was 0.128 and it is 100. So when you simplify this, it will come this much 0.336. Okay, is it clear to everyone, right? Hello.
Yes, sir. Yes, sir. Yes, sir.
Someone is saying anything, its voice is cutting down. So can you speak up again? Hello.
Yes, sir.
Okay. So see this problem and quickly do in 1 minute. Okay, it will work 1 minute. See this.
Yes, sir.
Okay, we will start. Here the length of the bar is given already. So L naught is 2 meter here, and is made up of steel and stress strain diagram is given. So from here to here, it is the elastic zone. And I want to tell you one thing. if loading is in the plastic region, so let's suppose this is the stress strain diagram. So let's suppose it elastic, when you remove load, and it will retract its path, and no deformation, it will regain its initial position. Okay, but when it is in the plastic region, so what will happen? Then whenever we remove the load, we know if it is the above the yield stress, then some plastic deformation remains there. So how much deformation remains there? That is the problem here. Hmm? So let's suppose this, and this always follow the path of this Young's modulus loop. What this loop signifies? This is the E, right? Hello.
Yes.
So whatever the stress, it will retract its path parallel to the this E line. So this keep in mind and try to solve this problem. Okay. Hello. So here it is given like yield stress of the steel is 250 megapascal. This is the yield stress. So this will be the 250 megapascal. And the Young's modulus is 2 into 10 to the power 5 megapascal. This Young modulus means its slope E. 2 into 10 to the power 5 megapascal. And due to the axial load bar being elongated by 6.5 mm. So delta L it is given by 6.5 mm. We don't know this 6.5 mm lies outside of this elastic zone or inside the elastic zone. That first we have to find. So the load has been removed. Find the change in the length of the bar after removing the load. What the problem? Hello. Hello.
Yes, sir.
Hmm. So first we will find like till elastic limit what maximum deformation is possible. If it would be the above of that maximum limit, then there would be some plastic deformation remaining after the removal of load. And if this 6.5 mm is less than the elastic limit, then no permanent deformation is there. Okay. So first we are finding. So how will you find like what maximum deformation is possible till here? What is the strain at yield point?
Oh, yes, sir.
Hello? Yeah, yeah, what are you telling? Tell, any problem? Hello? Okay. So strain at the yield point, what would be this? Stress by Young's modulus. Stress is 250, Young modulus is 2 into 10 to the power 5. Unit is the same, so we can simply get this. Strain is how much? Mm,
Uh, Sir, 1250 micron.
1.25 into 10 power minus 3. This will come, right? Mm. So this will be a strain at yield point. So what would be the maximum length, maximum deformation is possible till yield point is strain into that length. So strain is this and length is 2, so it will become 4 mm. Maximum deformation possible is 4 mm, but it is 6.5 mm. So what we come to know, like it is the outside of this, right?
Yes, sir.
Huh.
The 2.5 mm.
What 2.5 mm?
The deformation extra. That is the deformation which will be remaining after the load is removed.
सर मेरा तो 2 आ रहा है केवल.
It would be the 2.5, right? 2.5 mm. 1.25 into 2. 2.5 would be there, right?
Oh, okay, okay.
So this would be the 2.5. So now let's suppose this is the low. This is the strain at which this 6.5 mm deformation is there, right? Hello, hello.
Yes, sir.
So when you remove the load, then what path will you follow? This will follow this path. So what value of this and what is this? Can anyone tell?
So why we multiply it by 2?
Because this is the strain and we want to get the length. And what is the strain? Deformation by initial length. So deformation how will you find? The strain multiplied by initial length. Initial length is 2 meter.
Okay, sir.
So this is the our loaded condition, and this is the strain at that point. And then we remove the load. It will follow the path of this slope, and it will come to this. Means this is the which strain is this? Recovery. This is the recovery strain. Recovery strain. And this one is plastic strain. Recovery we
2.004, sir.
either we can say it elastic strain. How much answer you are telling?
2.004 meters.
2.004 meter. How it will come into meter?
Sir, because 2.5 mm will be
Oh, sorry. Okay.
raised
You
to
are
low.
telling length, na?
Yes.
Final change in you have to tell the change in length, not total length.
Then it will be a 4 mm.
Ah, okay. So we'll try. So how will you find this elastic strain? This would be the here. What would be the stress due to because it is the plastic same straight line is came. So this would also be the same as the yield point, right? Hello. Someone respond. Its value would be the stress value would be the same as the yield point, right?
Yes, sir.
Hmm. So
Yes, sir.
stress we know and Young's modulus we know, so we can easily get the recovery strain. So recovery strain would be the same as this because its stress is same. If now its variation is there, some white stress will go this way and some variation is there, then you have to find the exact value of that. But here we can easily get this much. This much is there. So we got this, and we know the strain. Now we can easily get the how much distance it got recovered. So it would be also the same because delta L is this and multiply with 2. So this much length it will get recovered 2.5 mm. So how much unrecovered unrecovered elongated length? It would be the initial elongation is 6.5 and whatever is has got recovered it would be not from there, so it will become 4 mm only, right? So now it may ask like what is the how much length has been got recovered, that may also be known, may also be asked. And here what I said, it is the straight line, so we took the 250 megapascal only. So now same problem, but here what happened, 1 minute, I will draw
Sir,
this.
excuse me, sir.
uh,
Sir, in the previous problem, actually, you told it's a straight line, sir.
this one
Which
na.
yes, which means that even though we apply more load than the required stress, it will be 250 only, sir.
Yeah, it means like it's now perfectly plastic material after this. Means you if you applied load till 250 megapascal, it will behave like as perfectly elastic. And after that 250, you if you don't apply load, even though it will keep on increasing its length. Means applying with no load, there is strain is there. So sometimes water is also treated as this. So water sometimes when we apply some very small load, so it will keep on flowing, right? Once you apply load and remove in water, you push and remove, though no force is there, but it keep on flowing, right?
Yes, sir.
So with no load, strain is there, but in water we used to deal with strain rate. So I just took the example of water because it's somewhat liquid there. So here also plastic, perfectly plastic material is this, perfectly plastic with no load, there is a strain. So whenever you ask like what is the stress strain diagram for perfectly plastic material, this is the stress strain diagram. With no load, strain would be there. Okay.
Yes,
So
sir.
how can the elastic strain come after the plastic strain?
Not getting what are you saying?
You have drawn the elastic strain is come after the
No,
plastic
no, it
strain.
hasn't came. Actually, what happens? You took the one rubber band. Okay, you stretched it. It became like this much length. Huh? When you remove, it will come back, right? Hello.
So, yes, sir.
It will come back, but if you now take the rubber band, remove, stretch it very long. Now again it will come back, but may not be its initial position, somewhat less, right?
Yes,
Same thing happens here. When you took the material, stretched it, and then removed the load, so some length it will recover. How much length it will recover? That we have found here, right? Got it or not? Hello.
Yes, sir.
Uh, so here it's a very same problem variation of this we have took in the next problem. There what I did, this young modulus is different, and here again different young modulus with another slope h came. Just see this. Here what I did, I will explain and you just take the screenshot and tell me the answer in the next class for this problem. So this is the problem, and till here, till 100 megapascal, it's linearly varying, and it's a Young's modulus is 75 GPa here. Okay, and after this, its Young's modulus got changed. It became 12 GPa only. Okay, got the problem or not? Stress, strain, same problem. So change the final, find the final change in the length after the removal of the load. Hello.
Yes, sir.
Hello. Actually, your network is very poor. I'm not
Oh,
able
yes,
to
sir.
hear.
Got it, sir.
Got it, no? So try to
Yes,
solve
sir.
this problem and let me know the answer. So it is the homework. Take it screenshot and try. Okay. Same problem. Here you have to find the first stress, which portion it is, and from there you have to come down. Okay.
Sure, sir.
Okay. So should I go forward?
Okay, sir.
So okay, this problem will
So,
solve. Uh,
sir, previous slide, sir.
what?
Sorry, take.
Uh,
Sir, go to previous slide, sir. I need to take screenshot.
okay. This one, now.
Okay, sir. No, no, sir. Over, sir. Thank you, sir.
So this problem we'll do in the next class, because in after that it would be much better, I think. So try this problem and then we'll stop. Just see, don't try. Actually, effect it may not come. You just let me know in between. I will ask, so it would be better. Just read once and then we'll start. Should I start?
Yes, sir.
Have anyone got like how we can proceed? Hello. Okay, then we'll start. So in here the figure in the this way, 1 minute. Figure is this, okay? So just keep in mind. The figure shows the three metal cubes ABC of dimension 100 mm. All three are same. Cubes are in the direct contact and the resting on the rigid base. Base it is as you put. and kept in the x direction. So this is the x direction as input. The upper face of the central cube is subjected to uniform compressive stress of 0.5 kilonewton per mm square. Okay, so this has been given. Now then we have to find the for the cube B. In between this cube we have to find direct stress in x direction. What is the x direction? This is the x direction. Okay, this direction you have to find the stress. And strain in xyz direction. In all three directions we have to find the strain and the volumetric strain for the B. For all things we have to find the for the cube B. So any idea how we can proceed? It may be wrong, you just try. Hello. Okay. So first of all I will try to make the video of all three. So let's suppose this is the first cube and this is the second cube and this is the third cube. Okay. So A, B and C. So here one thing it will come like stress will come.
Sir, Rahul,
Yeah. What are you saying? Hello. Hello. Okay. So here what I did in B load is there, right? In Z direction. Correct? Hello.
yes, sir.
So due to this what will happen? It will try to push this and it's try to change its dimension and then it will push these blocks, right? Because this dimension will change but those supports will not able to will not give permission to change this dimension, right or wrong? So due to this here some compressive stress in this direction will come, right or not? This is the sigma z and this would be the sigma x. So reaction of this will come to this because strain has been restrained in this direction, so sigma x would be there. Same way sigma x would be here and same way sigma x would be here also. Is this okay to everyone or not? First tell me this. Hello.
Yes, sir.
So here what I have got, here what I have got and here what I have got. Like sigma x would be here, okay. So what about sigma y and sigma z in this cube? It would be here or not? Hello.
It would be
It will be 0.
Sigma y and sigma z. What would be sigma y in for block A? What is the y direction? First tell me. Y direction is outward of your mobile screen or inward of your mobile screen, right? So in that direction, that block may expand or contract. It is possible, right? No restriction on that. So it would be 0 because no restriction on the strain. So stress would be 0 that direction, right? Correct or not? Hello.
Sir.
Same way with for the Z here. In Z direction, no stress, no load is there. In this
Yes,
downside
sir.
is there, but upside is nothing, no restriction. So that will also be 0. And same will happen with C, right? Sigma x would be there, sigma y no nothing would be there, and sigma z not be there. For the B, what will happen? Let me know. Sigma x is there. What will happen with sigma y and sigma z?
Sigma y and sigma z both would be there.
Why sigma y would be there? Here
So
also,
why
na
not?
So only sigma z, sir.
sigma x would be there, sigma z would be there, sigma y won't be there, right?
Sir,
Hello.
why sigma y won't be there? Hello?
Mm-hmm.
Why sigma y won't be there, sir?
Actually, in y direction, no restriction is there, na? It may expand its direction, dimension in y direction, right?
Ah,
So strain would be there. I'm not saying like strain won't be there. Stress is not there. I'm saying.
okay,
Okay.
हाँ.
Okay. So first question is the like you have to find the direct stress in the direction x, and these properties has been given. So we will use that. So any idea now how I can proceed? Anyone can tell? Now one broad idea I have given how to proceed for the first problem. Now you can easily see like in x direction whether the total length of the system will change or not. Let me know. This is the x direction. In x direction whether the total length of the system will change or not.
No.
It will not change, right? Because it is rigid on both sides. So the it will be 0. Means strain in this direction it 0. It would be the 0. Correct? Hello.
Yes.
So what would be the total strain in this direction? Epsilon A, epsilon of strain of A in direction x, right? And strain of B in direction x and strain of C in direction x. It would summation of x direction strain would be the 0. Correct? This is okay to all, no?
Yes.
Hmm. So what is the loading condition of this? A. We will find the
Sigma y.
sigma y and sigma g is 0 here in A. Only sigma x
Sigma
is
by
there.
is.
Only sigma x is there, and that one is the compressive one, right? Because this is here compressive, so we will try to get expand, and so but it is not possible, so compressive stress will come due to reaction of this compressive stress is here, right? So for this minus sigma x by E of A, correct or not? Hello.
Yes,
Yes,
sir.
sir.
And sigma y and sigma z are 0, so that part won't come. If that would be there, then with mu that will also come, right? Hello.
Yes, sir.
Now coming to the epsilon of bx, strain of b in direction x. So how will you find? In b loading, you see the loading first. Forget about a and c, just see only b. Sigma x and sigma z are there. So what is the sigma x? Due to this is the longitudinal loading, because in that direction we have to find. So this would be the sigma x by eb, right? Here eb will come because young modulus of b we have to take because in the body b. Now what will come? Due to sigma 2, it is in the transverse direction. Minus sign will also put minus, and here minus will come, minus minus will become plus, and mu of sigma 2 by, and sorry, it's not 2, sigma z by eb, and sigma y is 0. So this is okay to all or not? Let me know first that. Hello.
Okay, sir. Yes, sir.
For everyone it is okay, right? So in the same way, epsilon of c in the direction x we can easily find like what would be this? Minus sigma x by ec, right? It would be 0. Here we know the value of mu. This is mu for what? Mu of b would be there, right? Because mu of mu is different for different. So we know the EA, EB, EC and sigma 2 mu b. Everything we know. Here only sigma x is the variable, right? Hello.
sir.
So let me know the what is the value of sigma x. EA is 150, EC is 150, EB is 200 kilonewton per mm square, and this is also given in kilonewton per mm square. So simply sigma x will come in kilonewton per mm square. Let me know what is the value. You are doing right or not?
Is it 0.041?
Now 0.041, right?
Yes.
Kilonewton per mm square. One more person can confirm, and then will proceed further.
Yes, sir, I'm getting same.
Okay. So this would be the stress in the x direction, right? Now the direct strain in the x, y, z, all three direction we have to find. For what? For only block B now. Okay. This is also for block B, but it is the same for all these two also, right? Because sigma x due to the reaction of that it will come. Now coming to the block B only. Here what we have to find? Uh, should I go forward and wait? What someone is doing, then I can wait for 1 or 2 more minutes. Then we'll start. Or I go start. I shall start. Hello. Hello.
Yes, continue, sir.
Okay. Okay. So now what I'm saying, we have to find epsilon x, epsilon y, epsilon g for the block B only. Okay. So what would be the epsilon x? I will just write the its formula type, and you let me know the value. Okay. And if any problem is there, then let me know. I will explain. So for the x direction in block B, it would be the sigma x by B. Sorry, EB. Sigma x by EB, and sign you put properly. I'm writing like just general formula, and minus mu sigma g by eb. Is it right? Hello. It is mu b, and epsilon y in direction b would be minus mu b would be outside, and because y direction no stress is there, so only due to the transverse stress strain would be coming in the y direction. So it would be the sigma x by eb and plus sigma z by eb. And what would be then the z direction? Loading is there, so due to that sigma z by eb it will come, and it one is the in the transverse direction, so it will be minus mu b and sigma x by eb. Is it correct?
Yes, sir.
So values are not important here now. Just I want to let you know the what is the procedure here. That is more important. That is clear, right? Clear to everyone. Values anyhow you can get sigma x you knows that you put in the negative with negative sign, okay? Because here stress we are writing and direction we have already considered. That's why it came positive. Okay. So this is compressive stress. So here with the proper sign you need to put. Okay. So some value will come. I will give those value to answer value to you, and you match with yours. And now I am quickly finishing. Uh, so what would be the third? Volumetric strain. Any idea how you can find the volumetric strain?
Sir, have forgotten kindly.
Hmm?
Using a hook law.
Hello.
Can we
So
add
you
strain in all direction?
Can we add what after that? What you told?
No. Can we add strain in x, y, and z direction
So
for
volumetric strain is nothing. It is the for the anything like for the cube at least. For cube or cuboid, like suppose it's A, B, and it's C. So how volumetric strain used to find? Volume is ABC. Take the log on both sides. Ln V is ln A plus ln B plus ln C. So take make the differentiation. So dV by V would be the dA by A plus dB by B plus dC by C. So dV by V is what? Volumetric strain, right? And dA by A is strain in A direction. And dV by B is strain in B direction. dC is by C is strain in C direction. Yeah, correct or not?
Yes.
So simply for in order to find the volumetric strain in the cube, we simply add the strain in all three directions. So here epsilon x volumetric strain in B would be the linear strain in B in x direction, linear strain in y direction of B, and linear strain of in z direction of B. So if we know the value of these, then simply we can find this, right?
Huh.
So this is the problem. So this type of problem we can think of. So it's a value. Okay, so it would be the homework we can say this problem, this part. So you can also let me know the value of these in the next class. Is it okay?
Okay.
Or
Okay.
hello?
Okay. Okay,
okay,
sir.
sir.
Okay. So 1 minute. We are finishing with this for today. Check first.